So first, thanks for this opportunity to present my work or my opinions. I apologize because I was preparing all of this at a rather short notice, so it is not properly rehearsed. Additionally, I read my particularly. Do you see my cursor?
Yes.
Particularly the specifications we will use. I switch possibly to another form of the cursor, which could be more useful. Then I discuss proving correctness and proving completeness of programs. And then the very core of the presentation, systematic construction of programs. At the end, we have some comments and conclusions. Well, what I'm discussing here, it may be simple issues and rather obvious, but they are seldom discussed and seldom made explicit. I should be able to survive any questions and interruptions, so do not hesitate to ask if you feel it's necessary. So, logic programming, it was introduced as a declarative programming paradigm, and its implementation is Prolog. However, it seems that this declarative aspect is often neglected, or at least partly neglected, diminished. Here is an example from a text. There is a factorial program, and the explanation in the book is as follows. It is in terms of that we start doing something, and we continue on some other values, and we repeat until we achieve some target. And in this, we simulate the bottom-up computation. We store some values in some parameters. We remember some values in some the value of m in the mth step. And here is the program. And here is its declarative description. What is important? Logic programming is relational programming, and it is important which relations the predicates, the procedures describe. And here is such a specification. It has 4 arguments. If this one is smaller than this one and greater than 0, then f is a multiplication of f prime times all those consecutive numbers. If we have such a view as a program, then we do understand it. And if we have such a view, I would claim that we don't understand. With this specification, we can more or less formally reason or prove that it is correct. Now, the very notion of program correctness in logic programming. In imperative programming, the crucial notion is partial correctness. If the program terminates, then the results are correct. In logic programming, due to its non-deterministic nature, this notion splits into 2, into correctness and completeness. Correctness means that the answers of the program are correct. They are right, they are as required. And completeness means that all the required answers are answers of the program. All the required answers are computed. And I would call full correctness the conjunction of correctness and completeness. Full correctness or correctness plus. And here some basics about the terminology and the notation. Well, a program is a set of clauses like that with possibly empty bodies. And a body is a query, is a conjunction of atoms. And I use logical terminology. Atom is an atomic formula, not the Prolog terminology. And the operational semantics, the Prolog implementation, the SLB resolution, tells us how to obtain answers for an initial query. And an answer is an appropriate instance of the query. We do not need to distinguish computer and correct answers because due to soundness and completeness of SLD resolution. We use a standard notation of logic, so double turn style. If this is a program or a theory, then this means A is a logical consequence of P. It's true in all the models of P. And if this is an interpretation, then such an expression means that A is true in this interpretation. And the least Herbert model of a program is the set of all ground atoms that are logical consequences of the program. And we usually skip mentioning that here we have ground atoms because we will not use other kind of sets, I suppose. So before we consider correctness and completeness, we need to consider specifications. Because, well, correctness is with respect to a specification. As logic programming is relational programming, so a logic programmer has to understand the relations defined by her program. So specification should describe those relations. For each predicate symbol, there is a relation of ground terms. So it is convenient to express a specification as a Herbrand interpretation, a set of ground atoms. For instance, this is a specification for a member procedure, for member procedure or member predicate. The second argument is a list of one or more elements, and the first argument is one element of this list. So it is a clear description of a list membership. Technically, such a specification describes a relation for each predicate symbol. For each predicate symbol, those tuples for which P of the tuple is in the specification, this set is the relation defined by the specification S for the symbol P. Note that in logic programming, such specifications play the role of loop invariants or of assertions from imperative programming. Such assertions, especially such loop invariants, they are crucial for understanding imperative programs. And basically, I would say you don't understand your imperative program if you do not understand its assertions, especially its loop invariants. And as Furia, Meyer, and Welder wrote in Computing Surveys, even if programmers have not known about loop invariants, if they understand their programs, they are relying on some informal, intuitive notion of invariant anyway, like Monsieur Jourdain of Molière, who spoke prose without knowing it. And in logic programming, to understand a program, you need to understand the relation it defines. If you don't, I would claim you don't understand the program. So let us come to correctness, to the full correctness of programs. Assume that S is a specification, we have a program, and so we say that the program is correct with respect to the specification if the least Herbert model of the program is the subset of the specification. Whatever ground answer the program computes, it is in the specification. P is complete when whatever ground answer the specification requires is in the least Herbert model. Note that these notions are declarative. They are independent from any operational semantics. And the idea of logic and control, logic plus control, works as full correctness is independent from control. So when we establish correctness of the program, then any changes of correctness and completeness of the program, then any changes of control do not harm the full correctness. This slide, I skip it, relates, or maybe I quickly, it relates the actual program answers, which are general, which are maybe non-ground, to the notions of correctness and completeness. If the program is correct with respect to specification, then any answer of the program is true in the specification. Otherwise, if P is complete, then if some answer is true in the specification, then it is an answer of the program under some not so restrictive conditions. So an example of for specification, correctness, and completeness. So let us take list appending. This describes the list appending relation. Such triples, the three guys are lists, and this is the concatenation of those two. One style of writing this, another style of writing the same. Here we have the standard append program. The program is complete within this specification. Any triple of two lists and their concatenation is there. Strangely enough, it is not correct. And here is a counterexample. This is clearly not in the specification. Well, as we know, the program does not define the list appending relation exactly. It defines a certain superset. There were even opinions that this is a wrong program. It should be changed. It is not. And this fact is explained here. Here we have three specifications under which the program is correct. Maybe this is most interesting. It says that this is a list. And if this or this is a list, then all of them are lists, and this is the concatenation of those two. Such a conditional specification, such a conditional expressing of the specification gives a superset of the previous relation. And when the program is correct with respect to this specification, then whenever we use append to concatenate lists or split a list or some other useful tasks, then it works as it should. Questions? So the example of append shows that often we have our specifications approximate. We have one specification for completeness, another specification for correctness. Those atoms should not be produced by the program, otherwise the program is erroneous. Those is not correct. These atoms are required to be computed because otherwise the program is not complete. We need them, we disallow them. And this gray area, it is simply irrelevant. It is not important for us how the append program behaves on non-lists. So approximate specification is a pair. Specification for completeness, specification for correctness. This is a subset of that. And the full correctness is, this is a subset of the least-Herbrand model, and the least-Herbrand model is a subset of this. The least-Herbrand model is somewhere here. This is the border of the least-Herbrand model. When we build a program, we don't know in advance whether some atom from here should be computed or not. Moreover, the actual semantics of the program, the actual Lee-Herbrand model of the program, may differ in various implementations of the same task, various programs for the same task, or at various stages of a program development. So actually using exact specification could be counterproductive. Here is a comment that this shows that the idea of building programs by semantic preserving program transformations is or may be too restrictive. And I have a paper which shows an example where it is crucial that the semantics changes at the stages of a program development. Another approximate specific. Let us go through this. So here we have insert procedure, insert predicate, which is a part of insertion sort. The purpose is to insert a number into a sorted list. Should we accept, but what should happen when the list is not sorted? Well, the answer is irrelevant. So such an atom should be between the specification for completeness and that for correctness. It should be in the gray area. So here I have two formulations of that specification. This specification for completeness describes the relation we should compute. The specification for correctness may be explained as a union of the specification for completeness. And those atoms where n is not a number, or this is not a sorted list of integers. Or we can write the same set by using an implication in the description. If n is a number and L is a sorted list of numbers, then the whole triple is in this relation. So now I finished the story about specifications, a good moment for asking questions or complaining. And now how we reason about full correctness of programs, how we prove correctness, how do we prove completeness. For proving program correctness, we have the simplest theorem of logic programming. It is here. If P is true in the specification understood as an interpretation, then P is correct with respect to the specification. And here is the full detail of that theorem. Deransar attributes this theorem to a report of Clark in 1979. A more practical view on this is here. That means that for each ground instance, like that, for any clause of the program, if those guys are in the specification, then the head is in the specification. This theorem provides a declarative way to prove a declarative property of programs, which is program correctness. This theorem should be well known, but it is unacknowledged. It is generally unknown. It was presented in the textbook by Hogger and some other papers. But instead of using that, more complicated methods were proposed. Methods based on operational semantics of LD resolution, SLD resolution with Prolog selection rule, on pre and post conditions. So for instance, the work of Bossi and Coco, the important textbook of APT, important monograph about the theory of logic programming. They followed the work of myself and Małuszyński, where we first invented this style of thinking, and then we came to the conclusion that it is that we have this simple method. So we focus the whole paper about proving runtime properties, not properties of declarative properties of programs. So this is how to prove program correctness. Here we have an example proof with all the boring details. So here's the method, the sufficient condition for correctness. Here we have a program, and here we have a specification. And the property we want to prove is that the length of those two arguments, that the arguments are lists, and the length of those two differs by at most 1. So we have to apply that to all the clauses of the program. For this, it holds trivially. This is clearly in S. And to prove for that, we need to consider a ground instance of this clause. The ground instance is here. We have to assume that the body is in the specification, and we have to show that the head is in the specification. So assume this, the body is in the specification. Then all the 3 arguments here, they are lists. So that part is already proved. Let M be the length difference of those 2 guys. M is either 0 or 1, according to what we wrote here. Now let us look at those lengths and their difference. The length of that minus length of that is the 1 plus the length of T2 minus length T2. This is 1 minus M, 1 minus 0 or 1. It is again 0 or 1. So the head is in S. The proof is done. The program is correct with respect to the specification. Let me skip good moment for questions. I'm skipping the other examples. And I would like to mention that such proofs are similar to informal reasoning about program by a competent declarative programmer. And I claim that they may be performed in practice at various levels of formality. In particular, at a quite informal level in everyday programmers' practice. So let me jump to reason about completeness. The first thing is really interesting, namely, the subject has been neglected. Hardly anybody bothered about completeness of logic programs. Here are some exceptions. Hoger in the textbook and Kowalski in his paper, they defined the concept of completeness, but they didn't show any ways of reasoning about it. Abt in his textbook, well, had some other property which kind of partly played the role of completeness. So let us go to completeness. I would like to represent completeness as semi-completeness and termination. Technical notions. I would say that program is complete for a query Q with respect to specification S if it produces all the required answers for Q. So all the answers that Q requires for that the specification requires for Q. Technically, for any ground Q, any ground instance of Q, if this instance is true in the specification, then it is an answer for the problem. And the program is semi-complete if P, whenever terminates, produces all the required answers. Here, I wrote it more technically. And an obvious lemma, if P is semi-complete with respect to S, and P terminates under some selection rule for each query in S, each atomic ground query in S, then P is complete with respect to S. So knowing that completeness means semi-completeness plus termination, I focus on proving semi-completeness. I say, and this is an old definition of Shapiro used in debugging of programs incompleteness. A ground atom H is covered by a program with respect to a specification if there is a ground instance of a clause of the program, H arrow A1 up to AN, maybe 0, and maybe 0. And in this instance, all those guys are in S, in the specification. In other words, a covered atom can be produced by a clause of P from atoms required to be produced. And here we have a sufficient condition for semi-completeness. If each atom from S is covered with respect to S by the program, then the program is semi-complete with respect to S. We prove termination and we have completeness. Here I have an example, the append program and the previous specification of append. Take such atom, an atom from the specification. We need to show, for showing that the program is semi-complete, we have to show that H is covered by the program with respect to the specification. Two cases, we see two cases. First case, the list here is empty. Then this atom, those two guys must be the same, and this atom is covered clearly by, there is no body, and this atom belongs to the specification without any premises. The second case, K is not empty. And this is a concatenation of those two. So such H is ahead of this clause. And those two guys appended together produce M prime, so this atom is in the specification. The atom is covered by this clause instance. So this is semi-complete. We know that P terminates. We prove that the program is complete. Maybe I skip this. So comments about proving full correctness. In my opinion, those conditions for correctness and semi-completeness are, first, they are declarative. They abstract from the operational semantics, except for the termination. But termination of program is usually needed anyway. So we have to reason about to fix termination somehow. And they are simple. Just do compare it with 4 rules for imperative programs, where we prove correctness of imperative programs. They, I would claim, correspond to a natural way of thinking by a declarative programmer. They can be used in everyday programming at various levels of informality. And they provide a guide how to reason about programs. So now, I hope I'm well audible and there are no questions. A good moment for questions because I'm switching to the next chapter. Could anyone say anything so I know that I am connected?
We are here. Great.
So now I'm jumping to the core of the story. Constructing fully correct programs. We start from I show how to construct a program for an approximate specification, which is fully correct with respect to the specification. The method is as follows. Construct clauses so that each atom from the specification of completeness, each ground atom that has to be produced is covered by some clause. So it can be produced by some clause out of atoms which are in the specification, out of atoms which have to be produced. Now, each clause we construct should satisfy the sufficient condition for correctness, so we do not produce incorrect atoms. If those two conditions are fulfilled, then we obtain a program that is correct and semi-complete with respect to S. This is not enough because such useless clauses are possible. So, additionally, we should require that the clauses satisfy some sufficient condition for termination. This is the least formal part of the approach. Informally, we just want that here we have smaller term and here we have bigger terms. And as a result, we obtain a program that is fully correct. That means correct and complete. And the full description of the method is from my paper of 2018, and the full description is in a one-page report available from my page. So here's one example of constructing a program. Splitting a list into its odd and even numbered elements. So this is a specification which use those functions, odd elements of a list and even elements of a list. So we have a list, the list of its odd elements and the list of its even elements. Here is an example of some atom in the specification, 1, 2, 4, 5, 1, 3, 5, 2, 4. And we will construct a program that is fully correct with respect to this specification. It is an unusual case where our specification is exact. Here is the summary of the approach repeated. Here is our specification. So we need to cover each atom in the specification. We see that there are two kinds of elements in S. A specific one, where we have the empty list here, and there is nothing to do there, and just this unit ground clause does the work, and the clause is correct with respect to the specification. And the other case, where the list is not empty, it has a head, it has a tail. If it has a head and a tail, here we have its odd elements, here we have its even elements, but it is convenient to represent them in terms of T. So the even elements of this list are odd elements of this list, and odd elements of this list is H, and then even elements of T. So now we need a clause that on the right that has elements of S in the right hand. We need some suitable body, a body which consists of atoms in S. For terminations, we should use subterms of those terms. So good idea is to use this T, like that. Well, if we have T here, then the next two arguments are OE of T and EE of T, like that. Having this body atom proposal and this head, we have a suggestion that such a clause is a ground instance of some clause in the program. So for this A arrow B being an instance of a clause, the clause should look like that. It's a very reasonable decision. In this way, each such A, like here, is covered by this clause with respect to S. C2 is true with respect to the specification. If this is in the specification, then this is in the specification. The program of those two clauses terminates for any query, like that, for any query where this is a list. So the program is correct and complete with respect to S. We systematically constructed a fully correct program out of its specification. I have further examples, and I'm not late, I suppose. So I would say that this method is rather obvious. It can be applied informally to practical programming tasks. We may use just different levels of formality. In my opinion, it is just good practices of competent logic programmers made explicit. And also that I would like to point out, as you don't see it here, that approximate specifications are crucial.
I have a question.
Yes, please.
Can you go back to the previous slide?
Like that?
Right. So this is okay. Conceptually, this is, as you say, splitting a list into even of integers into even and odd integers. We need two of these clauses to do that. We have to check that the head is even, that we put it on the even list, or the head is odd.
No.
Am I missing something?
One clause. Even elements are those positioned at even positions. So, sorry. Oh,
Even and odd numbered elements.
yes.
Ooh, so it's a confusing.
Yes. I correctly wrote it here, but then just said even and odd for brevity.
The list of odd elements strikes me as the integers being odd, not the.
Yes. It's incorrect language, and the correct language is here.
Okay.
So I claim that it is useful for informal reasoning. So let me construct a program that permutes lists. So here is here's an informal specification that both for correctness and completeness, L prime is a list which is a permutation of list L. We need to produce every atom in the specification. For the empty case, it is easy. This clause, this unit clause would do. The remaining case is the first argument being non-empty list, head and tail. Well, what we know, if L, if we remove L, must contain H as an element, and if we remove H, then we get a permutation of T. So possibly we will need another relation that would describe this removing. So we will need some ins, A, E, L prime L, where L prime is L with element E removed. For completeness, for correctness, possibly we don't bother when this guy is not a list. So if L prime is a list, then it is L with E removed. So now let us construct, let us continue. Having such a ins predicate, having such an ins predicate, we can finish this clause. We have two, as I said, we have two premises. H is an element of L, and L with H removed is L1, and L1 is a permutation of T. Such a clause will be able to produce any two permuted lists out of two shorter permuted lists using this predicate. It remains to program this predicate. Oh, sorry. The first idea is consider empty list here and non-empty list here, but this is a bit counterproductive. A better idea is to consider the cases where E added to this list is at the beginning, and this unary clause, this unit clause does the work, or a case where E gets inserted somewhere into T. So here we have ins of, we insert E into T, obtaining T1. And here we have T1 as the tail of this list. Well, most likely we're done. And now any atom in this part, in this specification for completeness is covered by the those two clauses, this or that clause, and all those two clauses are correct with respect to this specification. If this is a list, then this is a list, then this is a list with when after E, with E being removed produces T, then this is a list from which removing E produces this one. The program is ready. So this was the same method, but treated more informally. Now, I would be glad to accept questions. I have some one or two more examples. One of them can be, one of them is computing the greatest common divisor. Another one is insertion sort. Another one discusses generalization, possible generalization of the approach to programs with negation, and as an example, an implementation of a definition of greatest common divisor. So, if you would prefer any particular of them, then I would follow you. Otherwise, I try to find another example, and I can show you. Sorry for that. Sorry. So this is the. So maybe let me come to greatest common divisor. Here is a specification. We are interested in such triples, which are numbers, natural numbers, such that these the greatest common divisor of those two. For correctness, we do not bother if one of them is, oh gosh, maybe, I'm not sure if this specification, we do not bother, if some of them is not a number, then we do not bother about the result. As you hear, I'm not sure if this is the right one. Okay, so let us construct the program. We have two kinds of elements of the specification for completeness. A simple case, and two first arguments are the same. Clearly, D must be, sorry for stupid error, of course, I should have n here because the greatest, and I should have small n here because the greatest common divisor of n and n is n itself. So correct this to n and this to n, and we are done. The second case is when those numbers differ. So an old truth that in border cases, this is where the errors are in programming and not only programming. Here is the simple border cases, and I made this error. The interesting case is those two numbers are different. And we can express GCD of two numbers in terms of smaller numbers using this property. GCD of those two guys is GCD of n modulo n and n. In this way, we have a hint for a clause of our program. This can be produced out of GCD of smaller numbers where n is the same and n1 is n modulo n. It's correct clause. It would produce this, but it's it may not support termination. To have it terminated, we need to take care that this is greater than that. Otherwise, n1 is n. Okay, but if we have that, then this we do not cover those atoms like this, where m is greater than n. For that, we add yet another clause. With this, we have a nice, efficient program for computing greatest common divisor. Okay, so that now there is not so much time left. So what I have here, I may have another examples, but maybe I would like to have a comment about generalizing the approach to normal programs. So, sorry for that. Oh, now I am visible. So this is a picture about our approximate specification for programs without negation. Those atoms have to be computed, those cannot be computed, those are irrelevant. If we add negation as failure, then clearly these will fail, and these will never fail because they have to succeed. So from the point of view of negation, we have such facts in a sense. So such a specific, and yet another comment. We have two sets to specify correctness and completeness of successes. But if it comes to negation, we have successes and failures. It looks like we need 4 sets. But what I said here, it suggests that actually 2 sets are enough because each of them plays 2 roles in a sense. These are required to succeed, and they say that their complement are allowed to fail. So such a specification, from the point of view of programs with negation, such a specification provides 2 conjugate specifications. Such a pair, seen as a specification for correctness, using some standard 4-valued logic, could be seen as this. Those guys are true, those are false, and those are true or false. And if we see it as a specification for completeness of a normal program, then it is like that. Those are true, those are false, as previously, but these are undefined. They are neither required to be true nor required to be false. And the approach I presented, it looks like it nicely generalizes to normal programs, at least with finite failure under Kuhn semantics. Semi-completeness could be generalized naturally, just that the program is complete for the queries which terminate and do not flounder in the general sense. So they terminate and they do not recursively call negation, and we do not have any floundering that makes the SLDNF forest building broken. And it is interesting that natural generalization of the conditions for correctness and semi-completeness that I showed produces conditions for correctness and semi-completeness for normal programs. It's quite lucky. When it comes to well-founded semantics, hopefully the situation is similar. The first step is that Ferrand and Deransart gave conditions for correctness of programs with respect to this kind of specifications under well-founded semantics. And hopefully, when we view the specification in this way, their condition would imply semi-completeness. But this I only checked superficially. So I should come to conclusions. I'm listening for your questions, but I hear that the set of questions is empty. So let me go. So my first comment are limitations of the approach. Specifications, as discussed here, they cannot express properties like for any T exists U such that P of TU is an answer of P. A specification as presented here has to provide an actual U. This, what I wrote here, I already said. The approach is rather inapplicable for answer set programming due to this limitation. In answer set programming, whenever we have many stable models, then it is crucial that we have different stable models. And so in one model, A may be true and B false. In another one, it may be the other way around. So due to reasons similar to what I wrote here, the specifications I discussed, they are inapplicable for ISP. And summary. I focused on declarative programming, so I prefer abstracting from any operational semantics. I showed how to prove full correctness and completeness, declaratively, with a minor exception for termination. The methods are simple, and they can be used informally in practical programming. This is what I believe. And I believe it's good to teach people to use those methods more or less formally in practical programming, when we teach programming, when we teach logic programming. It is important that we use approximate specifications. I would say that the concept of intended model is rather harmful, that it was especially how it was introduced in the context of declarative diagnosis or algorithmic debugging. And I believe it was main reason for non-acceptance of declarative diagnosis. Because assume you debug an insertion sort program. You do not know how elements should be inserted into non-sorted lists unless you have an approximate specification. Then you use specification for completeness in diagnosing incompleteness and the specification for correctness in diagnosing incorrectness. And the whole gray area is allowed when we diagnose correctness and is unnecessary when we diagnose incompleteness. And what we presented is a simple approach of constructing probably fully correct programs. And again, I believe that it can be used in practical programming, and it can be used at an informal level in teaching logic programming. Let me look. There is no next slide. It should be thank you, but I didn't have time to introduce it here. So, full stop.